In the previous units, we have discussed that any signal, any arbitrary signals can be expressed as linear combinations of fundamental signals. We have considered the impulse signal, step signal, etc. for that purpose. But from this unit onwards, we are concentrating on sinusoidal signals, especially the compact form of sinusoidal signal, which is known as the complex exponential signal, right? Now, we are saying that any arbitrary signal can be expressed as the linear combination of complex exponential signals. And what is the advantage of that? That is what we are going to discuss in this video. Let us go into the video and watch what is the advantage of expressing a signal as the linear combination of complex exponential signals.
In the first and second unit, we have studied that we can approximate any arbitrary signal x of t as a combination of either our impulse signal delta of t or step signal u of t or any singularity signal or any basic signals, right? So that was the basic idea, right? How can we approximate any signal x of t? So it should be linear combination. So the word is very important. It should be the linear combination of del of t or u of t, right? So these are actually fundamental signals. So expressing these kind of complicated signals or complex signals in terms of fundamental signals help us to reduce the complexity in the analysis and make our analysis very easy, right? Now, in this particular continuous time Fourier series, the main idea is that we can express any signal x of t as a linear combination of complex exponential, right? Linear combination of e power st. So we can express x of t as a linear combination of e power st. So let us take x of t is equal to a1 into e power s1t plus a2 into e power s2t plus a3 into e power s3t. So in this way we can express any signal x of t as a linear combination of e power st. So these are all e power st with the different frequencies, right? And we have also some multiplier a1, a2, a3. If you multiply our e power st with some amplitude value and if you add them together, see, you have to keep in mind that here amplitude we can modify, frequency also we can modify. Why? Because it is here it is s1, here it is s2, here it is s3. So by changing the amplitude and frequency of the complex exponentials e power st and adding them together, we can create any signal x of t. So when I say this, you may have a doubt, is it possible to do like that? Can we add some e power st signals and we can create any signal? So I can give you an example in Desmos. So let us go to Desmos. This is the Desmos environment. I am trying to create some signal. For example, y1 is equal to maybe a1 sin x. Okay, y1 is equal to a1 sin x, right? And then another signal y2 is equal to a2 sin 2x, right? Sin 2x. Here you can see amplitude is a2 and the frequency is increased to 2x, right? And let us take one more signal, that is y3 is equal to a3 sin 3x, right? So you can see that there are three signals, right? There are three signals. This is the first signal a1 sin x, right? Here a1 is the amplitude and the frequency is given like this, right? Frequency is given like this. And coming to the next signal, so here you can see this is a2 sin 2x. Here the frequency is increased and amplitude is a2 now, right? And coming to this signal, here the frequency is further increased to 3x and the amplitude is a3, right? So we have three signals like this, right? Now what I am going to do is that I am going to add all these three signals. So y is equal to y1 plus y2 plus y3, right? So I'm going to add. So let us remove all the other signals to avoid confusion. See, you can see that when I add y is equal to y1 plus y2 plus y3, I am getting a new signal. See, I am representing a new signal as a linear combination of a1 sin x plus a2 sin 2x plus a3 sin 3x. By adding the different sine functions, I am creating a new signal. Now if I can increase the amplitude to different values, I can change the shape of the signal. See, by modifying the value of the amplitude, I can change the shape of the signal. See, I can even try to create a sawtooth wave. See, I can create a sawtooth wave simply using the sinusoidal signals. By adding 3 sinusoidal signal, I have created the sawtooth signal. Even I can change the frequency. For example, even I can change the frequency here to 4x. See, now when I have changed the frequency, the shape again changed. Maybe here I will change it to 5x, right? See, you can see maybe here I will change it to 6x, right? Now you can see how the variation in the frequency is affecting the shape of the signal. So, see, by changing the frequency value and amplitude value, we can create any signal using these 3 sine waves, right? So this is the basic idea. This is a kind of triangular signal, right? So I have created a triangular signal and a sawtooth signal by simply adding the sine wave. So this is the basic idea what Fourier also said, right? So from that we have got this equation. This is nothing but x of t is equal to a1 e power s1t. So I have explained it using the sine waves, but you can show the same thing using e power st also, right? Plus a2 into e power s2t plus a3 into e power s3t. So I can express any arbitrary signal x of t as a sum of complex exponentials. Don't say simply sum, it is a linear combination. You have to say that linear combination of e power st. So I can express any signal as a linear combination of e power st. Now what is the advantage of doing like this? So we know that our system is an LTI system. So what happen if I give, so this is an LTI system. So what happen if I give a1 e power s1t to the system? I will get an output. So what is the output? The output will be a1 h of s. What is this h of s? This is a modifier. This is the amplitude changer, right? So this, with respect to this value, the amplitude of e power st will be changed in the output, but you will get e power s1t in the output also. That is what we were trying to explain in the first video, right? Since e power st is the eigen function, output also will be e power s1t, right? Only the amplitude will be modified, right? So for this first a1 e power s1t, you will get a1 h of s into e power s1t, right? Now in another experiment, if I am giving a2 e power s2t into the system, what I will get from the system? I will get a2 into h of s into e power s2t. Because of the eigenfunction property, you will get the same e power s2t in the output, right? Here you have given e power s2t in the input, you will get the same e power s2t in the output also. Now if I give our a3 e power s3t into the input, what I will get? I will get a3 h of s into e power s3t in the output, right? So this is because of the linearity property, linear time invariant system. Our system under consideration is linear time invariant system, right? So if you multiply something with the input, the same thing will be multiplied in the output, right? So if you multiply with a2, output also will be multiplied with a2. If you multiply with a3, output also will be multiplied with a3. But we have an additional h of s that is changing the amplitude of the e power st in the output, and that is known as the eigenvalue of the system. So how can we say about the output and input? If x of t is a linear combination of complex exponential e power s1t plus a2 into e power s2t plus a3 into e power s3t. If this is the case, if we can express the input as a linear combination of complex exponential, then because of the linearity and time invariance, we can express the output y of t as a1 into h of s1 into e power s1t plus a2 into h of s2 e power s2t plus a3 into h of s3 e power s3t, right? So you can express like this. This is the basic idea of continuous time Fourier series. So if you have a LTI system like this, right, and if you are giving an x of t, where the x of t is nothing but linear combination of complex exponential, then I will get a y of t in the output. That y of t will be the linear combination of e power st itself with some modifier h of s1, right, h of s1, h of s2, h of s3, like that, right? So from this we can conclude that if the input, right, if the input of an LTI system is represented as a linear combination of complex exponential, then the output also can be represented as a linear combination of the same complex exponentials multiplied with some complex constant value h of s. That is the conclusion we get from this particular idea. So don't forget where s is equal to sigma plus j omega. So this is the damping parameter. This is the damping parameter which we have studied in the first unit, and this is the frequency parameter. So with respect to this, the sinusoidal frequency will vary, right? So far we were discussing about this complex frequency. So this S is known as the complex frequency, but actually from now we are changing our attention to a special case of S, that is S is equal to 0 plus j omega. So what is meaning of this? We are considering sigma is equal to 0. Why we are considering sigma is equal to 0? We know that when sigma is negative, our signal will go like this, right? And when sigma is positive, our signal will go like this, right? So such signals we are not considering. Decaying signals, sinusoidally decaying or sinusoidally growing signals, we are not considering. We are considering only the sinusoidal signal, right? When sigma is equal to 0, what happened to the signal? The signal will be a sinusoidal signal, right? Sinusoidally rotating signal, right? So we are changing our concentration only to such signals, and we are trying to say that we can express any signal x of t as a linear combination of such signals, that is the sinusoidal signals, right? Sinusoidal signals. That is what Fourier said. Any signal x of t can be expressed as a linear combination of sinusoidal signals, right? That led to the basic idea of continuous time Fourier series. That is what we are going to see in the next video.
I hope you got a clear idea about expressing the input signal and output signals in terms of complex exponential signals. Actually, this is the basic idea of continuous time Fourier series. This helps us to look the signal from the frequency domain perspective, and this gives us a new look into the signal from the frequency domain.